Good evening, everyone. Welcome to the monthly Tucson Amateur Astronomy Association meeting. We're so glad to have you here. We have people in person at the U of A, even though there are things that are going on campus tonight. We seem to have gotten along just fine in terms of parking and finding our way here. And so we're glad to be on campus. We have people also who are on Zoom and people who are on Facebook. And we're glad to have everyone with us. I'm May Smith, I'm TAAA president. And tonight we have Bob Rose, who's operating the camera. We have Pete Hermes, who's helping with tech. And we have Terry Lappin, who's going to be doing a lot of the run tech and also a lot of helping with questions at the end of the presentation. So I do need to ask people in the room, remind them to please not talk at all as long as we're in the meeting, because it does affect Zoom and sometimes you can't actually interpret what someone was saying through the Zoom message, and sometimes it's muddled and you can't, but sometimes you can really interpret what someone said. So don't say anything you don't want people to hear. We will ask that people use their chat functions or their type-in functions in order to ask questions. So if you're coming via Zoom or you're coming via Facebook, then please make sure to plan to type in or enter in your questions so that we get your question. We want to address everyone's question. We will have, of course, people on all three modalities for the questions. So, you know, of course, two modalities are going to need to be waiting while we do the other one. So you have to have a little patience sometimes to get your question answered. We appreciate so much your being with us tonight. And we have one of our favorite speakers with us, who's a member, Dr. Brad Schaefer, is going to talk with you tonight. And he is coming up here. Wonderful, Brad. Yes, he just said he didn't trip. I always think about that on those stairs, you know, when you're waiting for something to happen down here, you know, you always think, gee, I'll be the one who trips. So, but he didn't. And we're getting his computer set up here. And the microphone, I think, too.
Well, howdy. I'm going to tell you the story about a supernova here. It's a supernova. The story is going to go from, well, 1181, what's that, 840 or 40 years ago, something like that, from the year 1181 AD, and you have to specify the AD, up till actually some of the data here came in even actually about a month ago. It's a story where we're going to, the critical input is all highlighted from the ancient astronomers and from modern amateur astronomy. The professional part of this, it's all well and good and done in there, but it's not critical. It's for filling in the details. So we have a story here, which is not your usual that you'd get from a pro astronomer here. Anyway, so the story, I got to give a setup here about supernovae, in particular about the historical supernovae. It turns out there are only 5, count them 5, known, reliably known, historical reports in the ancient records of a supernova up in the sky. It's 5 times in the last millennium, actually the last 2 millennium that we have records. And there are 5 of them. They go, well, supernova 1006, fair enough. It's not a very well-known one, but it's actually a rather important one for many of us. Supernova 106 down in Lupus, okay. observed by the Chinese. All these were. You have the Crab supernova in the year 1054. And that's a famous one, justifiably famous. A large fraction of our knowledge of supernovae comes from the Crab. There are so many things like pulsars and expansions and how you ionize the interstellar medium and things like that. Then you also have the supernova in 1572, which is Tycho's supernova. Again, this is epical. Many of the things are known from it. And you have a little bit later, 1604, you have Kepler's supernova. These last two supernovae were also back in the time rather fundamental for altering humanity or the Western culture's view of the world, because back at the time they were ridden by Aristotle, and no, it was the Bible that had to be true. But here you had these two stars that came up in Tycho's and Kepler's that showed that the heavens can change. But Aristotle told you they can't change, but here they were. And so that was one of the things that broke the floodgate. It proved Aristotle wrong. And once you have that, then you can start looking, questioning, well, everything in Aristotle and Ptolemy and elsewhere. Now, you see that there's a fifth supernova here. There's one in 1181. And that's not a very well-known supernova at all. And the reason is because we don't have a supernova remnant for it. For the other four, we have good, classic, well-observed supernova remnants known for a very long time. And take a little bit of a visual look here because you're going to be comparing this with a later picture. Look at these things. You have arcs and you have bubbles and you have big circles and things like that, okay? So that's a visual appeal. This is what standard supernova remnants look like. So the observers in 1572 and elsewhere, they saw the supernova, and centuries later, we see the remnant left behind. That's what the shards of the explosion going out. Okay, and as part of the setup here, I'd like to highlight the supreme importance of these four supernovae that have historical records. It turns out that knowing the age of the supernova is vital for understanding things. You see, the trouble is here, modern astronomers, we can see supernova in faraway galaxies, and we can get pretty good observations on them, fair enough, but you only see the explosion part. And if you only see the explosion, well, you can determine the physics of the explosion, you know, this expanding shell pretty well, but you kind of don't know where they came from. The classic supernova type 1a progenitor problem, classic. And you don't know where they go to, these remnants. You don't know how they come to. So looking at distant supernovae in faraway galaxies or even nearby galaxies, you only get a really little small part of the picture, the explosion. Also, you have people looking with radio telescopes and optical telescopes and such like that. And we've found a variety of supernova remnants around the sky. Some number, something like 100 are known. Most of them are really pretty faint and don't show much. Well, the reason these are so easily invisible is because they're the ones that make for visible supernova that you get reported in the history are the same ones that are the closest to Earth, which means that you can examine these supernova remnants much better in fine detail. You can watch the expansion. You can find the pulsar. You can look for the proper motion of the pulsar. You know the age of the pulsar. And so for these remnants, the four here, which have the historical reports attached to them, are overriding importance. Probably the majority of what we know about the broad picture of supernova comes just from these four supernovae. And kind of highlighting the importance of supernova, supernova are omni-important everywhere in astrophysics. You know, once I had a challenge with a colleague to name an area of astrophysics where supernova really didn't matter. And we had to think a while, and we actually came up with one or two. They were kind of arcane little niches. Supernova are omni-important. And I try estimating by going through AppJ papers, and something like 10% of modern astrophysics is spent on topics and questions and queries more or less related to supernovae. So it's very important, and the most important of them are these four that have the remnants attached to them, okay? So you got to start wondering here, what's going on with supernova 1181? Well, the reason you guys haven't heard of this is because we don't have a remnant for it, so it hasn't been able to push to the fore, to show new types of supernovae or what have you. So that's what I'm going to be talking about here. That's just setting the importance of this. So I'm going to be telling the story of supernova 1181. And let me kind of go through, take you through from the early days up until about a couple of years ago, fairly fast, because largely, because we didn't have a remnant, there's not that much to tell, hate to say it. Well, clearly you got to start with back in the year 1181. What was America doing then? Actually, who knows? What were they doing in England? Or, well, we don't know. That's a long time ago. It's more than 800 years ago. But the Chinese had a large number of a whole bureaucracy whose job was to look at the night sky, to find omens, to tell the emperor what to do. And so they observed a guest star in the year 1181, starting in early August. Turns out this guest star was actually recognized independently by, in the southern China, in the southern Sung dynasty, in the northern China, in the Jin dynasty, and several times independently over in Japan. Okay, so you had three different groups all independently discovering this in early August 1181. And they actually left a lot of records for us. Fine. Now, those things stayed in these old books until, well, until people started trying to pull them out in the 1930s, for example. But it wasn't, this guest star of 1181 was only first realized that it had to be a supernova back in, well, what was it? It was 71 by Richard Stephenson. And his logic is simple and easy. His logic was that the records say that this star got really bright and it was visible for 185 days. The records actually specify that. And they also say that it did not move. And the only thing up in the sky that gets up to negative magnitudes, that doesn't move and is visible for that many days, it's a supernova. There's no other alternative. There you go. That's a proof. He's actually still correct on that. So Stephenson realized that these old records are actually of a supernova. And back at that time, all he could do was look at radio surveys, and actually a little later you had X-ray surveys you could check. And what you found, you could look for the supernova remnant. Hey, there was a nearby supernova only 800 years ago. There should be a bloody bright supernova. You know, this is something that was sufficiently, should have been sufficiently bright that Carl Jansky with his original antenna should have found it, like he did Cassiopeia. He should have found it way back when. But what Stephenson found, when you look in the area, it's in northern Cassiopeia. When you look in the area of northern Cassiopeia, you can find some really old and junky, faint, distant remnants, supernova remnants in the radio, for example. And none of them really work very well. So where's the remnant? Well, what Stephenson did was he did the best he could. It turns out one of those remnants with the name, well, 3C58, one of those remnants, was the best game in town. And so he declared that this is the likely remnant of the supernova of 1181, okay? And ever since, that's the only possible solution. And so people, even up until a year or two ago, that's what everyone had done. That's what you'll find on Wikipedia. That's what you'll find everywhere, okay? So the idea was that the candidate for the remnant of supernova 1181 is 3C58. Okay, fair enough. However, since the days of Stephenson, there's been a lot of work done on 3C58. And basically it was found that 3C58 really is much too old. It can't be the remnant. Okay, so we're back to ground zero. Okay, flashing a bit forward to the year 2013, you have a guy named Dana Patchick, and he discovers the weird PA30 nebula. And so here's a picture of it in the WISE data, infrared data, WISE satellite. And so he discovered this PA30. And quickly astronomers worked out that this has to be a supernova remnant and has to be from a supernova of order 800 years old. Okay, so up to here, so this is a story kind of taking it up to 2021. So we actually had discovered the remnant, and a little bit had been learned about it. So what I'm going to tell you about now is the sorts of observations made since then. Much of this is going to be work that I've worked on, although what I'll be telling you about here, all the spectroscopy work is not mine. I've just pulled it from the literature and from friends. And all of the supernova modeling work, that's not mine. I can understand it, but I can't do it. Okay, so here we have the basic story of supernova 1181. So let me start going into some of the details here. Just to show you what's going on, because a lot of the details are going to be important here. We have to go back and look at the original data. And for the original data, it turns out there are 8 different sources, 3 of which are Chinese dynastic annals. Each Chinese dynasty had, after they fall, they had annal writers, recorders, their historians go through and write summaries, which then get saved to today. And they were operating off of the old original records. And so you can't really look at the original records anymore. They've been long lost. However, the records have been written down into books, and then the books are copied and copied. So you can't see the original material, but you can see later books, which are presumably pretty fair copies of it. I think this particular one is from the 1700s. So that's the closest you can get to the original data for the Chinese records. Let me actually read to you to give you a good idea what's going on. This is from Stevenson's very definitive, wonderful book. And this is from the Wenjian Tongkao. And I'm not going to pronounce any of this right. Tough luck. Chongqi reign period, 8th year, 6th month, day Juzi. A guest star appeared in the Kuai lunar lodge, invading Xuanji. The divination was, a guest star is a baleful star, a messenger from heaven. It appears in heaven and is abnormal. The various houses it enters indicate fortune or disaster. When the star is large, the event will be great and the calamity profound. When the color is white, its allocated territory will experience war and death. Now this guest star has appeared, they're now talking about the one in particular. Now this guest star has appeared at Lodge Ziwei and beside the stars of Xuanji. It is appropriate to prepare for a messenger of treachery from the border barbarians invading our territory. And this is a reference to the Sung dynasty used to control all of China, then the usual Mongol hordes came down and conquered the northern China, and the Sung dynasty and the Jin dynasty were very much at war with each other. And so they're referring to, this is a text from the southern Sung, and they're referring to the Jin people as those barbarians, border barbarians that have invaded our territory. Continuing. It is also said that what appears in Kui Lunar Lodge means war, while treacherous ministers deceive and confuse the emperor. Who do you think that could be? Therefore, the messengers of the Jin slaves comes to wrangle, smitting letters and gifts. And indeed, just at the time this star appeared, the Jin did send an ambassador to the southern Sung. And the ambassador arrived, and as always, the ambassador is put up in what we would call guest houses just outside the walls of the imperial palace. You'll see all this reflected up there in the stars in a moment. On the day Jinzhao, the guest star guarded the star of Zhuangji. 9th year, 1st month, day Gui Kui, the guest star was no longer seen, disappeared. From the previous year, 6th month, day Zhuzi, until that time was a total of 185 days. They tell us the duration. Then it faded and hid itself. At this time, the slave messenger had been in the guest house for a long time, and at this point, he departed. So what you have is you have the arrival of the Jin ambassador staying in the guest house and then departing. Fortuitously was timed to match this this ambassador's visits and match what's up in the sky. And there were actually, from several centuries before, there were prognostications of this case, actually. And so it ended up guiding imperial policy with what you with how they handled the Jin ambassador. Okay, well, anyway, that's the Chinese, that's an example of the Chinese reports. We also have the reports of the supernova appeared in 5 different Japanese diaries and histories, okay? And it's always imperative for a historian to go back and check as original material as you can. Well, with Chinese things, you can't do much more than check at books copied into the 1700s and 1800s. But for the Japanese diaries, they still exist. The original ones, in the original handwritten calligraphy of the guy who wrote it back in the day in 1181. So last week, I was in Tokyo at the museum trying to get in to see one of those diaries. And the week before, I was in Kyoto trying to see, well, another one of the diaries. And what I was hoping to see was just, hey, historians were supposed to actually look at primary material, right? But I think I was way too naive in 2 different ways. One way was these scrolls are made on really very thin paper. It's 800-year-old paper. And they don't want to go have outsiders or anybody go and rolling the scroll looking for the correct thing, for the correct text. So that was a little naive of me to think I could just kind of wander on in and be shown, oh, well, here, we'll pull up the record for you. I was also naive in thinking that looking at it for me would do any good, because this is a arcane calligraphy, very idiosyncratic. It's very hard to learn. It's like sometimes there are people with really bad handwriting or different handwriting, and you have a hard time reading this. Also, I learned when I was there that that the actual records, the characters, are a mixture of archaic Chinese and archaic Japanese, all smashed together. And even if I knew Japanese or Chinese or could read the calligraphy, there ain't no way I could understand it. And there are very few people in the world who can understand this. So what happens for the original material, what we're doing is we are all operating off of a transcription from the scrolls. We're operating off the transcription of the scrolls that was put into modern Japanese back in the 1930s. And so everyone, me included, is operating off of the Japanese transcription and then, then translated into English. So I could not get very close to the original data here, but there you go. Well, there's actually quite a lot of data here that you get from these 8 different records. And most of this is doubly learned from multiple sources. Japan and China says the same thing, and so on. Okay, so what do we have here? We have the duration of visibility was 185 days, okay? We have that the peak brightness, reading between the lines, the peak brightness is roughly between Vega and Sirius. A typical argument was once it was likened to the brightness of Saturn. And people mentioned that when you look at it, you can see little rays coming from it. And that's the sort of optical distortions all eyes have when you look at a bright source. And you only see it when you look at stars brighter than roughly 0th magnitude. So that put a lower limit. Okay, so we have an approximate magnitude range. It was peaked probably somewhere between Vega and Sirius. Fair enough. Also, the records tell us that there was no motion. And that's vital for eliminating the possibility that it might have been a comet. Okay, fair enough. And it also tells us the position on the sky. It actually tells us quite a lot about the information on the position of the sky, multiply redundant in many of these different sources. So here's what you got from the ancient people. And it's actually a remarkably lot that you can go getting from this. Let's go, well, let's see. Let's go starting with one of the questions here, and that is, I'm going to make a proposal. This is basically Stephenson's claim that the supernova, or the guest star of 1181 was a supernova. And I've already told you the logic here. Only a galactic supernova can get that bright for 185 days with no motion. It's a supernova, case closed. And that actually is still correct. There's a loophole, I filled it, who cares? Okay, well, we do care, but no longer any need. Okay, we can also go from the observed peak brightness, we can go into, we can deduce what the peak magnitude was. And there are a variety of ways of doing it. I already sketched some. There's another way you can do it, and that is using information from later. You know the type of, it's a type 1AX, you know roughly the duration, and you can work backward from the duration to a peak magnitude. Okay, fair enough. So we go getting a peak magnitude. And this is going to be useful, very useful later, because for the remnant that I've already spilled the beans, we have a distance from Gaia, and so we can translate these peak magnitudes into an absolute magnitude at peak. And then that can be compared to theoretical models of the various supernova types. So this is actually kind of important for that. This is going to be the proof that it's a subluminous type 1AX. Okay, there we go. Well, here's another thing. You can start going using the position that they report. And well, that's going to be vital for trying to determine what the supernova remnant was. So this is the game that Richardson played back in the days when much less was known, where you had, where he identified 3C58 as being the remnant. Okay, now I'm going to go into this in some detail here, partly because I can go improving on Stephenson because we have more knowledge since Stephenson did this, and partly because a couple years ago, a group in Australia really butchered the whole stuff very, very badly. And that was the last published thing, and they just got everything wacko wrong. We'll meet this group again here in a little while. Okay, so there's good grounds for going back and revisiting the whole question of what is the position based on the original Chinese records. Okay. For this task, let me draw the scene again. And here's the scene. This is northern Cassiopeia. Well, actually, here is Cassiopeia, our traditional Cassiopeia. It's done in gray, fair enough. And there are various constellations around. So for, well, down here's Perseus and Cepheus, there we go. And they're Chinese constellations. They're fairly well known. There's some uncertainties in this. For example, the constellation Wang Liang, well, what this consists of is, well, a famous charioteer from before the Han Dynasty here. Oh boy. Anyway, this star, Beta Cas, represents Wang Liang, and he's a charioteer. And so he has a traditional 4 horses, and these are the reins going out to the 4 horses. But showing you the usual uncertainties, we aren't totally sure which of these 4 stars are the ones that were used by the astronomers back in old China. Turns out it doesn't matter in this case. But for example, here we have the constellation Xuanzhi. And that's an important one because we were told that the supernova invaded, was close to, the fifth star in Xuanzhi. Okay, well, what's the fifth star? Well, that depends on what the stars are in Xuanzhi. And it turns out in this case, we don't know very much. Going back and look at the old records, all we're kind of really told is it's a big, wide thing, and it's between Wangliang and Wagai. And so the two green depictions are plottings of the stars that are thought to be in the constellation by two separate definitive authorities. And this is basically telling us we aren't really sure exactly which stars are in Xuanzhi, so we don't really know which is the fifth star. Okay, so this is the setting. So somewhere around Xuanzhi is where the supernova blew up. Okay. Well, we have information from the old Chinese. They tell us that it appeared in the lunar lodge Kui. Okay, Kui is one of 28 lunar lodges in the sky. These are orange slice-shaped regions going from the North Pole to the South Pole. Of course, they didn't see the South Pole, but they define regions. And so the region, the edge of the regions are defined by particular stars. These are happen to be ones down in Andromeda and Pegasus. And so this is the region, the highlighted in cyan, is the region of Kui. And so the Chinese tell us that the supernova appeared inside Kui. So the thing is somewhere in that cyan region. Now, 3C58 is just barely inside the region. Barely is perfectly fine. That counts. And a little bit later, PA30, I've already told you that that's the answer. PA30 is also, well, just barely inside the region. So this sets the scene. So we kind of know what the right ascension of the supernova was in the day. Well, we have the information that it's invaded the fifth star of Xuanzhi. Now, invaded, well, it's a little wishy-washy, and you can take it as being, within something like a 1.5 degrees of the given star, okay? And well, which is the fifth star? Well, I don't know. You know, I can make cases for any of the stars which I have cyan circles around, okay? So for example, here's 1, 2, 3, 4, 5. Or you can count 1, 2, 3, 4, 5. Yeah, there are a lot of ways of doing this. So there are many different stars here, but the only ones that could be called fifth stars are in the cyan region here. Okay, so we have a bit of additional information as to what it is. We're also told that the supernova was in proximity to 3 separate constellations, Ziwei, Wangliang, and Wagai. Proximity, well, what does that mean? It means it's farther away than invaded. It's probably got to be more than 1.5 degrees away from, but there's no outer limit for what they would have called proximity. And here's a quick thing. They say both that there's proximity to Wangliang and to Ziwei. Actually, I should mention here, Ziwei is the outer wall of probably the biggest, most famous constellation in old Chinese times. It's the Imperial Palace. And here is a gap in here from that star to just up here. There's a gap in here. This is the main gate of the Imperial Palace. And just outside the Imperial Palace is Xuanzhi. Xuanzhi is the guest houses. That's where the imperial ambassador was going to stay, okay? Or the Jin ambassador was going to stay, okay? Well, anyway, we're told that there's proximity both to Ziwei and Wangliang. Well, you know, that's a pretty wide region, and even the best you could have somewhere in here, you're still 5-7 degrees away from one or the other. So this proximity has to be kind of a loose thing, more than 7 or 8 degrees, within 7 or 8 degrees, something like that, all relatively loose. But you can draw the area where you would have proximity to Ziwei. And well, you can draw an area around in here, fair enough, like that. And you can draw an area which you would consider to be proximate or something like that to Wang Liang and here to Hawaii Gai. And you have a region where they all overlap right in here. And it's a fairly dark cyan region. And so only somewhere in this lens-shaped region would you have proximity to all three of those constellations, okay? And I note that, well, PA30, getting ahead of the game, I've already told you the answer. PA30 is, well, nicely placed, but 3C58 is outside the region. You could not really describe 3C58 or a supernova there as having any proximity to Z-Way. You'd have to go through 1, 2, 3 constellations to get there. And you wouldn't call it that. And in any way, you'd probably call it as being proximate or invading Gay Dao, which is not what they say. Okay, so we now have 3 constraints on the position of the supernova, and here's the joint constraint from it: greatly smaller region. And what happened was well, actually there are 2 groups, but the Australian group went off and claimed, with very bad logic and very bad data, they claimed, oh, it's somewhere a big, huge region up in here, and they're just all wrong, okay? So that's the justification for why I can go through and do a better modern analysis to try and find out where the position is. And the result is, yeah, you can really rule out 3C58, and yeah, PA30 is right where it should be. Also, you can say, there ain't nothing else there, guys. You know, no traditional type supernova remnant is there. And so that right there is already a proof that the supernova of 1181 is not any of the traditional types of supernovae. Okay, then in 2013, you had Dana Patchick come on. So his day job, he's a medical technician in one of the Los Angeles suburbs. And at nighttime, he takes off his glasses, puts on his cape, and he goes off. And what he's been doing is he's been searching for nebulae, mostly planetary nebulae, but nebulae of any type. The way or one of the primary ways in which he did it was he would take the WISE satellite, the WISE astronomical, it's an observatory, and it has a full sky survey in the infrared. And it's just, the survey's there. We all could have gone in and started looking through. A long drudgery job, but he did it. And he found a total of 41 different nebulae. And as like, you know, Messier M1, M57, and so on and so on. The name you give to these things is going to be the discoverer's name, or the initials of them. P was already taken, so he had to go to PA for Patchick. And then you add on an index number, okay? You know, M1, M57, and so on. So what he found was PA30, and here it is. This is the image from WISE. There's a bright, irrelevant star here, and right here is a central star, and it appears red because it's this picture is false colored for infrared, okay? So this is the nebula that he found. And he found a central star in there too. This is a round shell in Cassiopeia. Oh, the radius is a bit more than an arc minute. It depends on where you call the edge of this fuzzy edge here. And in the center was this really weird, very blue star, which everyone knew immediately was this is the star that made the shell. Okay, fine. Now, let me tell you a horror story here. We're just past Halloween here. Okay, so we have Patchick's 30th nebula, PA30. And it turned out in the year 2021, one of these Australian guys, a guy named Quentin Parker, went off and he tried in press releases and calling up journalists and things like that, he tried to say that this nebula and star is Parker's star, with the obvious idea that PA stands for Parker, not Patchick. And he's been going around ever since pushing, pushing in not nice ways. And I find this all horribly despicable. I don't want to use the word evil, but despicable probably is one that won't get me in a legal court. So anyways, this is kind of just showing you the sorts of things that at least one professional was trying to screw an amateur, and largely everyone else is just laughing at the guy. But he keeps calling up. For example, this morning I went and checked Wikipedia on Supernova 1181. And there was this long story about how Parker had discovered PA30, and it was dubbed Parker's star, okay? So it was a little bit of an experiment this morning. I went and changed it all in Wikipedia. And it'll be interesting to see how fast it's going to be until Parker gets on and tries changing things back to control history. Actually, maybe someone could go and check right now. Maybe he's already done it. You know, he's always hops on these things. Anyway, so so this really is Patchick 30, and it's Patchick's discovery, and it's this one discovery that made the case. Without this, even today, we'd still have no idea what's going on with 1181, and it would be just a supernova with no remnant. And there you go. So Patchick is the great hero here. Now, in optical light, working with Patchick, George Jacobi here locally went off to one of the Kitt Peak telescopes. He took a picture. Here's a picture of it. This is that same bright star in the middle. This is the central star. And maybe you can see, well, can anyone really see it? You know, you got to fuzz your eyes. And there's a faint nebulosity around in here, okay? It's really got to be pretty faint. So it's bright in the infrared, faint in the optical, and that's a little bit confusing because a nearby recent supernova really should be blowing us away in the optical, but it's not, okay? So this is, again, telling us that this is not your usual, this is not your grandma's supernova remnant. Okay, there's something unusual going on here. It's not normal. Okay, whereupon all this started happening, various professionals started getting in the game and taking spectra and doing all the things that professionals can do pretty well. And what they found, just looking at the central star, what you find is that the central star, well, actually, here's the spectrum of it, okay? And there is, it's just all emission lines, and they're very broad emission lines. And they're very high excitation. Oxygen 6, that implies incredibly hot central stars. And the width of this particular line gives you a velocity. So what you have to be looking at is you have to be looking at this remnant, the left behind star at the center of the supernova is blowing a stellar wind. That's what creates these lines. It's blowing a stellar wind. And the width of this line can tell you how fast the wind is blowing. And the wind is blowing 16,000 kilometers per second. When I read this, my jaw dropped. And that's the basic thing that the pros do. Because 16,000 kilometers a second, that's completely unprecedented. You know, a nova eruption gives you, typically about 1,000 kilometers a second. Supernova, you never get above 8,000 kilometers a second or so. This is twice as fast. You know, people like me suddenly start wondering, is it possible that you can be blowing a wind that fast? We all agree that it has to. Can't think of any alternative. So what you have here is already, you have a wacko, weird, totally unique, unprecedented star at the center of Patchick 30, okay? And it's something wacko, not understood going on. Okay, you start finding other things about the central star. First off, it's incredibly hot. In fact, the temperature starts becoming meaningless because it's actually a non-thermal spectrum. But it's hot, really mother hot. Another thing you find when you take the spectrum, you can take the spectrum in the optical, and people have done it also in the X-ray. You find that the composition does not have any hydrogen or helium. Yeah, that's what the universe is made of, right? But no hydrogen or helium. This is not a planetary nebula, for example, but you knew that already from the velocity. But the real composition It's almost entirely carbon, oxygen, and neon. It's about 13% neon. Where do you get neon of that purity? Anywhere in nature. That might be the purity you get from going to Times Square and looking at the neon light bulbs. Neon, 13%. You just don't get that. And there's one exception, and that's in the core of a very massive star, or if that core gets later put into a white dwarf. It's the only way you can get that pure of a neon. And the only way you can get those things out there is with a supernova. So that right there already is a proof that Patchick 30, PA30, it's a supernova remnant. It's the only way you can get that neon out there, much less at the high velocity, okay? Let's see, also you can prove that the central star is very luminous. And well, this has actually utility too, because the central star is very luminous. It's not a black hole, guys. And it's not a neutron star. And that right there tells you a lot, because it's got to be a supernova. That's the only way you can get these properties. It's not a supernova, but it's not a supernova like anything we know of, because all the common garden variety of supernova out there, they leave behind either a neutron star or a black hole. Here you have something that is neither. So this supernova cannot be any of your garden variety supernova. It's got to be something weird and rare, which is what we're coming up to here in a moment. Okay, so already we're getting a good picture of what's going on with this. Now here's one thing that I had a good fun with. Hey, I'm the world's most frequent and best user, or something like that, of the Harvard plate stacks. I spent a large fraction of my lifetime at the Harvard looking through plates and checking brightnesses of stars. I probably looked through fractions of a million plates already, measuring magnitude estimates. And so whenever I hear whenever I hear of weird, wacko stars like this, my immediate thinking is, well, let's see. Can I look for this on the Harvard plates? I do this much too much. And here you have a star, which in modern times is something like 15th magnitude, maybe 16th magnitude. And 800 years before, it had to have been much, much brighter. So it's fading on the time scale of 800 years. And so if you look back over the previous century, you might be able to spot it fading. And that'll be a little bit more proof that, that this is a central star of a supernova. And so I went back to the Harvard plates and found, well, here's what you find. Here's a plate from 1924. Here's that bright star off to one side. There's the counterpart. And here's a plate from 1950. And you can see that you can get good magnitudes from this. These old plates are actually quite good. I've lost almost all of my data that ever was saved on mag tapes. That's all gone. No one has it. But the old plates, they still work. Anyway, you can see the main point here already. Let's compare the brightness of that star to the brightness of this other star just down below the bright star. Here you can see in 1924, it's a lot brighter than this nearby comparison star, okay? A lot brighter. Over here, the brightnesses are comparable. Well, maybe this is a little bit brighter, but it's comparable. And that shows that from 1924 to 1950, the star faded. And that right there was what I was looking for, and you got it here. Okay, so I've come up with a light curve from it. I was actually able to find it on 40, 50, it was something like 48 plates I found it on in Harvard from 1889. Wow, I got data from 1889. This is history. This is historical data. This is no longer modern astronomy. This is history. This is what a historian does. So I have Harvard plates from 1889 to 1950. Here's light curve for it. Fading like mad. And this is something you can take to the bank and demand that a theorist have their models be able to reproduce. Hey, I'm an observer. I can chortle at the conundrums I'm giving to the poor theorists. Well, okay, so the Harvard plates are all calibrated in a very particular way. And if you're trying to look for modest magnitudes you have the question, what happens between 1950 and now? 73 years. Okay, fair enough. What's it been doing since then? But to get modern data, to plot on a plot like this, you have to have it identically calibrated to the old data. You have to use basically APAS comparison stars, and it has to be the classic Johnson B magnitude filter. And largely, there's no data out there that you can compare. The pros aren't doing this. Oh, they're looking off in the new Sloan R and I, you know, which you can't compare. You can't get color terms well enough. So it turns out I basically have found no professional data that you can go comparing with the Harvard B band magnitudes. So I've been able to find it from two different ways. One is Arnie from the AAVSO. Arnie Hendon has the APAS survey, and it's him that defined the comparison stars that were used here, and it was definitely B magnitude. He was very careful to always calibrate off of the Landolts. So the AAVSO magnitudes right in here can be directly compared to the old Harvard data. So we've added this point here, and apparently it's gone flat or something, like who knows what it's been doing, but on average, it's been relatively flat here. Fair enough. But that's only, 2011. You'd like to find out what it's been doing recently. And you can't use TESS data. TESS is in some ill-defined red magnitude. You can't compare anything with it. And so there's no other data. The pros just haven't been doing it. Now, what I could have done is I could have put in, waited, at the time it would have been waited 4 months, put in a proposal to Kitt Peak to go get observations on Kitt Peak if they were open. And then, it would have taken, half a year to find out whether my proposal was accepted, and maybe, it'll be a year before I ever get data. And that's only if I'm lucky and get the clear skies. So I was at a loss to know how to get more data to extend it from then to now, from 2011 to now. But what I went off and did was I have worked with a variety of top quality amateurs, actually a number of them around the world, but the ones I went to, a guy named Josh Hampsch and Tony Van Munster, they were both in Belgium, effectively, and said, hey, could you go off, and I had to give very specific specifications, which comparison stars to use, what filters to use, and things like that. And said, hey, could you go back and take some observations of this central star? And they said, sure. And the next day I had my data. It was wonderful. And so this data here is the amateurs, and you can see that it's gone back to fading fading relatively fast here, and there you go. Now, so what we have is a grand light curve of how many years is it? 134 years. 134 years. Just the existence of a light curve like this is rather awesome. You don't get that sort of thing in almost any astronomy. But here we have 134 years. And what you see is, again, totally unprecedented. You have a secular falling of a star over 134 years. And things like that, there ain't no other star in the sky that does anything like it, okay? So yet again, we have supernova 1181 just being off the charts and weird. Oh, I should actually mention a little bit here that this variation here is probably intrinsic to the star. This is not measurement errors. This is actually the star going up and down on timescales of days. And I know that because this is a question that TESS can answer. TESS is a spacecraft up there that produces these wonderful light curves. And so here is, I think it's like a 20-day interval, something like that. And I've binned it up here. Actually, the data in here is, I think, if I recall right, it's 20-second time resolution. 20 seconds. You could sit here and we could hold our breath that long. Wonderful data. And it shows that the star is varying up and down, basically chaotically. And it doesn't have fast variations. but there you go. Or variations much faster than a day. The critical part from the TESS observations is you can run a Fourier transform on this, and you can prove that there ain't no periodicity in it. There's no periodic modulation, and that's going to come back and haunt one set of theorists here a little later, because if the star with a big, the white dwarf with a big wind, if it had a close-in companion star, you'd see it here. Okay, TESS data is wonderful, and you don't see it. This is the proof that the star does not have a binary companion, well, in the current day. Okay, so the TESS data worked wonderfully for this. Okay, so far I've only been talking about the central star. Let's start talking about the nebula. Okay, so PA30 consists of a central star with a bright star next to it, and then the nebula around it. So the central star is wacko weird. The nebula is also completely unique, unprecedented, weird, and again, people like me just drop our jaws and say, "Oh, how can that be?" And nothing like it's ever been seen. Okay, so people have gone off and taken spectra and pictures of the nebula, and in the X-ray, you find the thing's mother bright in the X-ray. Huh, how'd that happen? It means the gas material, at least part of it, has to be incredibly hot. But how can it be that hot 800 years later? It means something is powering and brightening it, okay? And we don't see things like that. It's not like the Crab Nebula has these sort of temperatures. There you go. Okay, you can also do spectroscopy on it, both optical and X-ray. And what you find is that the nebula is composed of, well, basically carbon, oxygen, and neon. No hydrogen, no helium. And so again, you're left with the dilemma. This is undoubtedly the ejecta. What we're measuring here is undoubtedly the ejecta from the supernova. And so it could well be different from the ejecta in the fast ongoing stellar wind deep inside. But again, the original stuff is 13% neon? Where'd that come from? Nothing like this has ever been seen, even vaguely anywhere. By a variety of methods, you can show that the nebula is around 900 years old, for example, by watching the expansion age. And you can get the expansion velocity. The expansion velocity you can get either by radial velocity of the lines or by knowing the distance and looking at the proper motion, the size of the nebula. The expansion velocity is 1,100 kilometers a second, greatly down from the 16,000 kilometers a second that you have from the stellar wind being given off by the stellar remnant, the white dwarf in the middle. So what you have here is the picture is you have this outer nebula, which is blown out and being blown out at a low velocity, blown out at a low velocity. That's a very low velocity for a type for any supernova, with one exception. We'll get to that in a moment. So you have a relatively low velocity ejecta from the supernova, and then deep in the middle, as this thing is still expanding, you spark off a white dwarf with this ferocious stellar wind, just blasting away, a wind blowing, and it breaks up, it impacts into this thing, heating it up, and you'll see the filaments from it here in a moment. But you have this low expansion velocity, and this velocity really has to be the supernova expansion velocity. And that ain't your typical supernova. Remember, supernova have a typical expansion velocity of 8,000 kilometers a second. There's only a couple known supernovae that have expansion velocities that low. Okay. Oh, here's another point I forgot. You can measure the mass in the nebula. It's 1/10 of a solar mass. Ha! That's greatly too large to be a planetary nebula. It's greatly too small to be any other type of supernova, or at least a conventional type of supernova. So yet again, we're realizing that this isn't your grandma's supernova, okay? And then with Rob Feason, we went off to, took pictures at Kitt Peak here. This is from the MDM. This is the picture. Wow. Look at those filaments, just. And the only thing I can, again, this is another one of these jaw-dropping times. Rob, when he wrote down, when he analyzed, reduced the data, sent it along, and I'm not sure I've ever quite been lost for words as long as I was, and he had, again, ain't nothing like this. Okay, and the thing that this most reminds me of is a fireworks display. Here's one of those chrysanthemum fireworks going off in all directions you see on the 4th of July. So again, what is this? And they all come right out of this star in the middle. Well, just to quickly say what I think has to be going on here is you had the basic shell that was ejected by the supernova at 1,100 kilometers a second way back in the year 1181. And it expanded out. And then you had this wind ignited, blasting away at 16,000 kilometers per second, just blowing through here. And and that wind will break up the expanding shell into knots, and then Raleigh-Taylor instability, and then it will shred them out in the wind. So I think that's what's going on here. But again, no one's ever seen anything even vaguely like this. Okay, so let me start making some propositions to you for how we understand what's going on here. Well, the next proposition is that PA30 is a supernova remnant. Well, I've already gone over that. This is now a no-brainer. Ain't no way you can get a large amount, high abundance of neon, much less going at high velocities, other than something that we would all call a supernova. Okay, so PA30, supernova remnant, done. Okay. Now, you can also go and connect PA30 being the remnant of supernova 1181. And there we have the age of PA30 happens to, within reasonable error bars, equal the age back to 1181. It's pretty good proof right there. Another part is ain't nothing else in that Chinese error box. And so we got to be pretty confident that this is the only possible candidate. And then you have a coincidence between what the peak magnitudes would be as observed by the Chinese and as required by modern theory applied to the remnant. So we can be pretty confident that PA30 is indeed the remnant of supernova 1181. So the next question, now we're getting into astrophysics that starts becoming very useful. What type of supernova was supernova 1181? Okay, well, we have the Chinese records, and they provide a lot of information which tell us, for example, the peak brightness. The peak brightness, well, we have a Gaia distance, and I've got the Gaia distance, and I can tell you what the absolute magnitude was at peak. And the absolute magnitude at peak was, well, give or take, call it minus 15. And that's 2 orders of magnitude fainter than most novae. So by all standards, it's a subluminous supernova, and it certainly is not any of the core collapse or type 1a supernova. It's something weird, it's something different, it's something unusual. We've been getting this all along. We actually can put a real value for what the peak absolute magnitude was. And we have a variety of other things. The expansion velocity is 11,000 kilometers a second, very low mass, and the central remnant is not a black hole or neutron star. So with these, we rule out basically every known type of supernova except for one. Okay, and so by elimination, it has to be a subluminous type 1AX supernova, is what it's called. Okay, and this is a rare class. Okay, the definite it's only been seen in 20 supernova now, most of them very poorly monitored. The trouble here is that these are subluminous supernovae. By subluminous, it means in the ordinary galaxies that you look out there, they're too faint to be picked up by the supernova discovery teams. Too faint, so they're just all missed. They could be happening very frequently, but you won't see them. So you can only see them in nearby galaxies, and then usually rather poorly. And so it hasn't been seen in most of them. Nevertheless, just by looking at the supernova data itself, the definition of this subluminous type 1ax supernova is you define it to be expansion velocities, well, around about 1,000 kilometers a second. Click, we're there. And an MV fainter than, minus 15 or so. Click, we're there. So by definition, this fits the type 1a supernova. And you can only get these because you know the age and because you know you have the Chinese observations of the peak magnitude. So you wouldn't have gotten any of this if you didn't have the Chinese and you didn't have Dana Patchick. There we go. So it's definitely a subluminous type 1ax supernova. Now, the subluminous type 1ax supernova, you can almost consider them, well, fizzled supernova, failed supernova. That's why they're subluminous. You don't get the full energy out that you might be able to get out in other comparable systems. There's something failed in some way about the supernova, okay? But because they're subluminous, the few that we see, we can only see them in relatively nearby samples. And so the number of them per galaxy has to be high. And there are substantial uncertainties, but maybe a quarter of all supernovae in any one galaxy is a subluminous type 1ax supernova. About a quarter of them, or some such number. So here we have one of the major components of supernovae, and largely, well, up until now, people don't have much in the way of good observations. We only recently learned that the whole class exists. Yeah. And we have no idea as to what causes them and so on. So that's this is what's making supernova 1181 important, because it's the only example where we can get good data of a dominant component of supernova in our universe. It's the only one where we can connect the supernova brightness, duration, and so on to the supernova remnant. It's the only one near enough that we can actually look real close in great detail at the remnant left behind and deduce all of its properties. This is the only case. So supernova 1181 is humanity's only hope for understanding, well, a quarter of all supernova out there. That's why supernova 1181 is so important. Okay, let me go back to a bit of a technical point here. You might recall that I have this light curve. Okay, it turns out that a guy named Ken Shen back at Berkeley, before all this, made a prediction about the behavior of the white dwarf remnant left behind by, well, in some models of type 1ax supernovae. And there's really weird physics going on. The wind is being powered by the decay of nickel, the radioactive decay of nickel. And if you know anything about this, you'd say, oh, wait a minute, the half-life is really short. How can it be powered this long after? And there's weird physics going on. And so it's well understood, basically, they're completely ionized, so you don't have electrons close to the nuclei, so you don't get the same rates that you would otherwise. So you could have this all powered, and he worked out models for how this would work. And here are his predictions of the various models tossed in here. Note this is a log scale. So in the first year or so, the central star fades fast and furious for the first year or two, but then it goes to a flat, and then it suddenly drops, and then, well, recovers a little bit. And this sudden drop can be out to, well, 800 years. 800 years right there. So it's looking to me like this is that. And so clearly a theorist going through and trying to fit this data with other things will be able to learn a lot of what's been going on. It's a hard and complicated problem, and people haven't done it yet. But you can be sure that Ken is out there slaving away running models, trying to get it to work. So this is coming our way. Well, I mentioned that we don't really know what a type 1a supernova is, or type 1ax supernova is. And, well, we don't. So here is an assortment of 6 different models of what people have proposed a type 1ax supernova should be like. And, well, okay, they're all wacko different. There is one commonality. They all involve basically an oxygen neon white dwarf. But other than that one commonality, you can stick an oxygen neon white dwarf into a myriad of settings, all wacko different, and you get something that people have claimed is going to give you a type 1ax supernova. Let me give you an example here, because this is going to be the one that I'm going to claim as the real solution. Model B is where you have a white dwarf in spiral. You have 2 white dwarfs, of which one is a carbon-oxygen white dwarf. That's the usual type. And the other one is an oxygen neon white dwarf. And by the usual binary evolution, they get close. Gravitational radiation causes them to lose angular momentum. They in-spiral. And at the last instant, they basically are going into a head-on collision. And the combined white dwarf is over the Chandrasekhar limit. And you get the carbon starts thermonuclear burning and very fast. And you have an explosion. And that's the explosion that's the supernova. But in this case, because these are not both carbon-oxygen white dwarfs, this one is an oxygen neon, you don't have that much carbon in the system. And so you get a fizzle or a weak supernova because you don't have as much carbon as you need for the traditional type 1a supernova. That's why they call it type 1ax, whatever. So of all these models in here, they're all over the place. And this is telling us we have no idea what a 1ax is. I'll tell you here in a moment. Well, I've already told you. Okay, so one of the things you can get from this is the realization that of all these types, they're all predicting a different remnant left behind. Well, they'll all have supernova shells going out in expansion, fine, but the stellar remnant left behind is going to be different in each case. For the bottom 3 here, what's left behind is a neutron star. In supernova 1181 ain't no neutron star. And here you have, well, it's left with basically a cataclysmic variable, an old nova. Oh, and that should be blatant. And supernova 1181 ain't that. And so you have 2 of these models, A and B, where you're left behind with one of these white dwarfs that could be blowing a vicious stellar wind. So both of these models match much of the data. And you have a hard time distinguishing which one of those 2 models will explain 1181. Well, the difference is the top model requires that there must be some relatively ordinary star pretty close in. And the test data already ruled that out. So it's not that, it's not that, not that, not that. There's only one model left, okay? So putting the summary up in a different way, okay, here you go. Here's trying to connect how you can go for each of these models, how they connect with the various observed data. And keep in mind, a lot of this comes from Chinese data, and a lot of this you wouldn't get unless you, well, actually, almost all of it you wouldn't have unless you have Dana Patchick's discovery. And so the clear winner is model B, where you have a carbon-oxygen white dwarf and an oxygen neon white dwarf in spiraling together. They get closer and closer. They finally do the hit each other, and they explode as a weak supernova. This is the only model that works out of all the ones presented. And there we go. We've gone from the Chinese data to being able actually to decide the nature, the physical model of a type 1ax supernova, which is perhaps something like 1/4 of all the supernova in any given galaxy. Okay. So let me summarize what we got here. You don't have to read this in too much detail, don't worry. This shows the various propositions, which I've just proven to you. It was a guest star, supernova 1180, or the guest star of 1181 was a supernova. PA30 is a supernova remnant. PA30 is the remnant of supernova 1181. Supernova 1181 is a subluminous type 1ax. And the only acceptable model is a merger of two white dwarfs of known composition. Wow. And, you know, without the history data, which is those two inputs in there, without the history data, would have nothing. You know, if PA30 was found without Patchick, or without the history data, it would just be another weird thing. We wouldn't really know what's going on. And without Patchick's discovery, well, the two critical points in here are the Chinese and Japanese data and Patchick. And amateurs have contributed yet more, and historical data has contributed more. Sure, there's good professional input in here from big telescopes and space observatories, but everything, the important things all come down to the old history and to amateur discoveries and observations. Okay, so why don't I stop there, but I will put up here a list of needed observations and needed models. Need not read this too much, don't worry about it. The point I'm trying to make with this final slide while we take questions is there's still a lot to know. This is early days yet, but this is where you go for the gold. This is where you get the information. This is going to pay for historical astronomy all by itself. So there's a lot to be learned here, and so keep tuned over the upcoming years. But there you go. So why don't we go to questions here?
We'll ask people in the room to raise their hands. Please wait till I get to you with the microphone so that you ask your question directly into the microphone, and everyone online then can understand what your question is. So raise your hand if you have a question.
Uh-oh.
I have an esoteric question for you. At the beautiful fireworks photograph from MDM, do you know, was it with the 2.4 meter?
2.4 meter at MDM.
Okay.
Yeah.
Made by?
Rob Thiessen was up there. He was doing it because I told him to.
Yeah, but the telescope was made by DFM, I believe.
That's right. That was a DFM telescope.
Yes.
Right.
Just wanted to point
Yeah,
that out.
I actually was there when Melcheimer came around and was working on doing repair work on it back in the day. Is Melcheimer still alive?
Yes, he is. I met him a couple of months ago.
Oh, wonderful. He's a fun guy.
Okay. Very serious. Thank you. That's just amazing.
Oh, indeed. It maybe we should all in unison drop our jaws.
Okay. We have some other questions here.
Maybe I missed it, but what is the distance of PA30?
2,300 light year parsecs, excuse me, 7,100 light years. And that distance is gotten by Gaia, because Gaia has a good parallax for the central star. So we know the distance pretty well.
Other questions in the room? Any hands? Okay, if I missed anyone, let me know. Oh, yes, there is one more here. It'll take me a minute to get there.
I thought I saw a hand raised back up there. Nope, okay. We're trying to give her exercise class.
So a few slides back, let's see, more, back. One more, right there. What's the difference? No, next, yeah. What's the difference between the different colors?
These are just different models here. So Ken Shen ran a variety of models. He didn't know at the time what the properties of supernova 1181 were. So he was running through the amount of carbon in his modeled stars. Some of them had more carbon, some of them had less. That made for different times in here. There were various other things that he was varying around to see how things varied.
Okay.
And so he didn't know the properties of 1181 to put in there. We now know them. So the differing models in here just shows you the range of possibilities. And again, no one would ever thought of anything like this. Ken Shen saw through it, because for people like me growing up, you know, the nickel decay that powers the supernova, we all know what its half-life is, and it ain't no 800-year no half-life. So how could you get nickel radioactive decay powering the thing even 800 years later? And Ken came up with this arcane thing that as soon as you describe it, you say, my gosh, I never thought of that. Well, and he's right. Oh, I can give the 2-sentence version of that. What you have is ordinary nickel 56 has electrons going around it, and it decays by electron capture in the nucleus. But if you put the nickel 56 into a completely highly ionized medium, you don't have the electrons going around it to go into the nucleus, so to speak, to create the nickel decay. So the nickel nuclei is stable. Whoa, who'd have thought?
All right, Facebook. Let's see what it says here. So this is from Matthew Brian Kenji, I think. The Yoa era in Japan was marked by famine from July 1181 through May 1182. In the capital, more than 42,300 people died of starvation in only 2 months. That coincides with that time period.
I did not find any evidence of that when I was reading through the transcription of some of the diaries, because they were more concerned with court politics of who was appointed who when. Another issue right around that time is that's just around the time of the start of the Kamakura shogunate. And the whole Japan was in turmoil and rebellion, all for around times in there.
Okay, also from the same person, I wonder why there's no European record of the supernova.
Why is there no European record of supernova 1181? Yes, you said it, the Dark Ages, but you got to be careful here. Yeah, I've had a lot of back and forth with European historians, and they don't like to be thought of as studying Dark Ages. And so, especially for the Crab supernova, oh, it's amazing the conniptions that the people will, the European historians will try to go through to explain why the Europeans couldn't have discovered the Crab supernova, or did, but it got lost, or did, but it's a stupid record over here. They'll go through all sorts of conniptions to, in my pop psychology, try and prove that no, the people we're studying weren't illiterate barbarians at all. And I think the same thing's happening for 1181.
Okay, and the last one from Zoom, would colliding white dwarfs have created any gravitational waves?
Oh, you bet they would have. Yeah.
And then it says, do colliding white dwarfs still adhere to the, I can't say that word limit, that one.
Chandrasekhar.
Yeah.
Well, the two colliding white dwarfs were both individually below the Chandrasekhar limit of 1.4 solar masses. But when they in spiral and they finally merge, the total mass is above the Chandrasekhar mass limit, and that's why it explodes. Because above that mass limit, you get the carbon can go thermonuclear burning, and that's a very fast runaway action, and it releases so much energy in a very short amount of time, it blows up. So yes, you would get huge amounts of gravitational radiation. And well, LIGO wasn't working then.
Okay, great. I think that's all the questions.
We had a question up in the back.
We have one in the back. Okay, I will be right there. Well, I'll be there in a minute or two, actually.
The May exercise program.
For historical context, this supernova was just before the start of the Third Crusade in terms of timeline for Europe. But an actual question, what's the actual role of carbon in terms of creating a supernova? I know that in normal, like there's the mass timeline and what changes within the star itself, but how does carbon change the outcome of the supernova?
Right. When carbon undergoes thermonuclear burning, which you can get when you get the mass sufficiently, well, above Chandrasekhar, such that you get an implosion, the remnant gets sufficiently packed that you can get thermonuclear burning. Carbon burning produces a relatively large amount of energy. Burning of oxygen or neon or whatever doesn't give you as much energy per nucleon. And so if you only have a bit of carbon that's doing the burning, you aren't going to get a powerful explosion. And so that's the idea here by these 1AXs, is you have your carbon oxygen white dwarf, which has got a lot of carbon in it, plus an oxygen neon white dwarf. And when the two combine, you don't have anywhere near as much carbon as usual. And so the explosion is relatively weak, which leads to it being low luminosity and so on, and small ejection velocities.
Okay, we have another question here.
Does dark energy have any effect on the expansion of that nova, that supernova?
Could you repeat?
Dark energy
Oh, no.
has any kind of effect on
No,
the,
it's irrelevant here. Nice try. But you got to keep thinking about these sorts of things because you never know where dark energy is going to pop up. Hey, I got a question back for you. You immediately told us about 1181 was around the time of the Third Crusade. Does that imply that you look young, you might be a student? Does that imply that you're a European history person? Oh.
I knew the 11th century was during, the 1100s for full of the Crusade, so it was just which two were it was near.
Fair enough.
Google answered it.
So. Yeah, I was actually worrying here when I was answering here that, gee, I wonder if there are any of those type in the audience here. But no, good.
Okay, let's check again now. Make sure, yes, we do have another question in the audience here. Good.
What is the mass of the remnant?
We don't know. It's probably, well, we don't know. We have a hard time seeing the white dwarf, which is doing all of this, because it's inside this shroud of this massive wind, which is going to be optically thick. And we don't have any object going around it to give you a Keplerian mass that way. So kind of the only way you have, well, it can't be too large, it can't be more than 1.4 solar masses, and it can't be too small, half a solar mass. And it can't be, well, then after that, the only other guidance you have for the mass of that star with the huge wind, the only other guidance you have is from theory, and they're all over the place anyway. So if push come to shove, I'd say 1 solar or 0.95 solar masses plus or minus 0.45.
Any other questions now? Okay, we have one question.
You mentioned something about Gaia. Is Gaia from the Indian? It's an Indian word. Gaia is like a goddess.
Well, actually, it is a Greek goddess. The name Gaia is a Greek goddess of Earth, I think. It's the basic Earth goddess. But it's also the name of a European satellite, a really awesome European satellite. They're very much like Hipparchus, except done better. So what Hipparchus is, what Gaia has done is they've gone off and they've scanned the entire sky many times over going down to, well, it depends on how you count, but let's call it 20th magnitude. And they have exquisite photometry and but astrometry for all or most of the stars in the sky down to 20th magnitude. And that's how you get the parallax to this star. You get the parallax to it, and you get the distance, and you get some photometry too. But Gaia is the European astrometry parallax satellite, which has produced some wonderful data.
Okay, last call for questions. Any other questions appear on Facebook or Zoom?
The Europeans also did not record the 1054 supernova, correct? I would claim correct. The Europeans do not have a record of the supernova 1054. Got to be careful here, because there have been, people in the historical supernova community, we get these papers all the time of random enthusiasts finding the crab in every record you can think of. And I've spent a lot of my own time reading through the entire Icelandic sagas and huge Byzantine monastic records, we can call it, and looking through entire annals from Kiev. That's what I've done. I've also done things about, Byzantine coins. But there's a cottage industry out there, and every couple of years, somebody comes around and claims they found the crab in some European record. And they're all really... Let me give you an example here. In the Irish annals of Clonmacnoise, I probably didn't pronounce that right either, there is a story that seen above the, this is for the year 1054, seen above a particular monastery there, they saw a large round circle with a cross in it, and large birds, like a rock almost, would fly up, land on the cross, and then come and swoop down, pick up greyhounds, and carry them away. That's about all you got. And that was claimed to be supernova 1054. That kind of shows you the quality of this. But let me come back and mention that I think there is one record which is reasonable. And officially, geographically, you can call it European. There's a report by Ibn Butlan, who is a Christian medical doctor high up in the Byzantine court in Constantinople. Constantinople, that means that it's European. But his report, that probably is the crab, came from Cairo. And that report probably is the supernova of 1054. It was associated with a huge plague that decimated the people in Cairo. Now, do you call Cairo being reported by someone from Constantinople? Constantinople is geographically Europe. Yeah, there you go. Culturally European. Do you call that a European mention? Well, we can argue, but maybe that's the closest we can come.
Brad, you have another Zoom question from Richard, which is, have you looked at Arab or Indian astronomy text?
I have not. Many other people have. And for those, I think the quintessential person is Richard Stevenson, the guy who wrote this book. He's still alive. He's not very active, but he's still alive. And he's incredibly impressive in many different ways. And he's had any number of, he reads old Arabic, and he's had any number of Arabic graduate students, and they've trolled through everything you can think of. So I think the Arabic data has been well covered. For the Indian data, I hate to say it, there's not that much data of these sorts of histories or annals or reports or records from India. The Indian astronomers were, let's say, interested in different things than reporting what was up in the sky, even casually. So I don't think there's much in the way of Indian data.
Thank you so much. We appreciate the interesting presentation, Brad. You always come up with such wonderfully interesting things to talk about. So thank you so much. And we're going to move to our next activity, which is we're going to have a few comments from Ed Foley about the 32-inch. Oh, we're going to say goodbye to Facebook. So we appreciate all of our Facebook people joining us for this meeting. We hope that you will visit us again the first Friday of any month at 6:30. And we also hope that you will look at our webpage at TucsonAstronomy.org, and you'll look around there and explore and find some interesting information. And if you have questions, send us these emails. So thank you so much for joining us. So